Section 5.7. The change of entropy in the surroundings. The change of entropy of this entire universe is equal to the change of entropy of the system plus the change of the entropy of the surroundings. How can we get the entropy change of the surroundings? Well, we'll just use this equation, the integral of dq surroundings over t surroundings. And remember, when we talk about surroundings, usually we refer to the immediate surroundings of the system. And usually it's just the air surrounding the system. And this t surroundings is often treated as a constant, the ambient temperature. And then we can take this t surroundings out of this integral. And then the integral of dq surroundings is simply q surroundings. Therefore, the change of the entropy of the surroundings is simply q of the surroundings over t of the surroundings. And this q surroundings is exactly negative q of the system. Therefore, we often use this equation to compute the entropy change of the surroundings. In particular, when we deal with isothermal process, because the system temperature remains constant, we assume that the surrounding temperature is equal to the system temperature. Otherwise, the temperature of a system will change until it's equal to the surrounding temperature. So for isothermal processes, we have the entropy change of the surroundings equal to negative q over t. Let's look at two numerical examples. First, let's calculate the entropy change of the entire universe when 1 mole ideal gas is reversibly compressed from 25 liters to 10 liters at a constant temperature. So whenever you see this constant temperature condition, we can assume the temperature surroundings is equal to the temperature of the system. Now, how can we compute the entropy change of the system? Because temperature is constant, the entropy change only depends on volume. We use this equation. We get the entropy change, negative 7.62 joule per K. How can we calculate the entropy change of the surroundings? Again, we get back to this equation and we realize that this t surroundings is simply t. And then we realize this q reversible is the integral of TdS. So really, we're looking at the negative integral TdS over t. And this t is constant. So on top, this t can be taken out of the integral, and it cancels with the t on the bottom. Therefore, the result is just negative integral ds. That's negative delta S. Well, we have the value of delta S, negative 7.62. Therefore, the entropy change of the surroundings is positive 7.62 joule per K. The entropy change of the universe is 0 in this reversible process. Again, the entropy change of the universe is always 0 if the process is reversible. Now let's look at another example problem. This time the compression is irreversible and P external is equal to the final pressure of the system. So how can we compute the entropy change of the system and the entropy change of the surroundings? If we just look at the system, in this irreversible process, its initial state and final state of the system is exactly the same as in this example problem 5.2. Same initial state, same final state. So, without doing any calculation, we know the entropy change of the system is negative 0.762 joule per K. We copy this number from here. It's very simple. This is because entropy is a state function. However, if it's an irreversible process, the Q in this problem is different from the Q in the previous problem. That does affect the entropy change of the surroundings. Again, we have to use this equation. The entropy change of the surroundings is negative Q over T surroundings. For an isothermal process, T surroundings is equal to T. So negative Q over T is the entropy change of the surroundings. Now let's do the calculation. We have this negative Q over T. And then negative Q is W minus delta U. Delta U is 0 because we're talking about ideal gases under constant temperature condition. So this is 0. And what about this W irreversible? It's simply negative P external times delta V. P external is the final pressure of the system, and this is delta V. All right, and then we can simplify the top part. We can say, well, this P final is simply nRT over V final, and then we can combine these two terms, and over here, this is of course the temperature of the surroundings. However, for the isothermal process, we assume the temperature of the surroundings is equal to the temperature of the system. So we can replace this with simply T. T and this T cancel. So on top, we have negative nR times, well, VF over VF. That's just 1. And then we have VI over VF. All right. Now we plug in numbers. VI over VF, initial over final, that's 25 over 10 minus 1. We have this 2.5 minus 1 here, times R, times the number of moles. The result is 12.47 joule per K. What about the entropy change of the universe? That's the sum of the entropy change of the system and the entropy change of the surroundings. Now we get the sum here, 4.85. It's greater than 0. It tells us the entropy change of the universe is positive. The entropy of the universe increases after this irreversible compression. And that makes sense.